Welcome to Chapter 10 for the Exercise Science, Sports Medicine, Fitness Technology, Research Methods course. Let me share my screen and get going. All right, so basic statistical concepts, right? So statistics are a subfield of mathematics useful for collecting, analyzing, interpreting, and presenting data. Again, if you have read any of the research that I've been asking you guys to read, you will see that in the methods section, there's a whole lot of statistical data to look at, right? This is how, when we do our experiments and we get numbers from the things that we measure, we can put them in and look at what the things such as averages or the differentiations that we're looking for. We're looking to see, is there any statistical significant difference between one group versus another group, or are they kind of the same, right? And so again, the statistics part, I know some of you, when you look at some of this stuff, you're like, oh my goodness, I'm getting overwhelmed. It's not overwhelming. You just, the more you dive into it, the more you get used to it, it's not as bad as it seems, right? So there's both description and inference, all right? So descriptive statistics are used to characterize a group based on data taken from the group. This would include measure of central tendency, the extent to which data clusters around a point, or variability, the extent to which data are spread out, right? So again, sometimes you'll see things grouped together, and sometimes you see things all over the place, right? Measures of central tendency, so the mean. Again, this is your, so when you're looking at your grades and what are your average grades, things like that. Median, single data value that resides right in the middle of the data distribution, such that half the scores fall above and half the scores are below, right? So it's the middle number, right, is the median, okay? And then the mode is the most frequent scoring and distribution, okay? So this could be, if you were looking at, say, NBA shots, right? And you're looking at, say you scored them from 1 is free throws, 2 is shots in the paint, 3 is 2-pointers outside the paint, and 4 is anything outside the 3-point range, right? You might find the mode to be, say, shots in the paint, right? Guys are driving in the hole mostly. Or, maybe you're looking team by team. You look at a team like Golden State, most of their shots are 3-pointers, between Curry and Thompson, and when they had Durant or something, a lot of 3-pointers being thrown up at that team versus another team that might be a driving team. You have another team that looks for open mid-range jumpers, right? You have another team that gets fouled a lot, so the number that comes up mostly might be 1 on that team. They shoot more free throws than anything else. So again, that'd be an example of the mode, right? The range, the difference between the high scores and the low scores. So this would be, like when I'm looking at people's tests and, the top score is 100, and the low score is like 75 or something like that, that'd be the range, right? Standard deviation is an estimate of the spread of the scores away from the mean, right? So, you could have a mean at, say, 80, and the standard deviation is, so what this shows, how to explain this? All right, so what this would show is if 80 is your mean and most of the scores were around 80, you're gonna have a very low standard deviation, So if every score, so say 5 people took the test, all 5 got an 80, you're not gonna have a standard deviation. Now, if the standard deviation is 80, and that's because out of, 6 students, 3 of them scored hundreds and 3 of them scored 60s or something like that, then you're going to have a standard deviation of close to 20, right? Because each one's 20 points away, or you're looking at, you had a few folks in the 90s, a few folks in the upper 60s or 70s, things like that. It's going to make that standard deviation smaller, right? So that's what that means, right? So it's how spread apart. Okay. Standard error, the mean estimate of the expected difference between the sample mean and the population mean. So this would be, you did a sample and you look at some spores and then you look at the population. How do they match up with your population, right? And so again, a low standard error would mean that you had a pretty good sample. High standard error would mean your sample does not represent the population very well. The goal is to collect data from participants in a research study, be able to generalize the findings to a larger population that the participants represent. So it's used to answer two types of questions. Is there a relationship between variables, right? So if we have an independent, dependent variable, and is there a difference across the conditions, right? So if we give different treatments and different, there's different conditions set up, what are the differences? Relationships between variables. Is there a relationship between GRE scores and successful performance for particular graduate programs, right? Why would we do that? We already got the GRE set up. Well, the question would be, is it really a good test? So if people are taking it and those that have the highest GRE scores don't necessarily finish graduate school or do well in graduate school, and those who are testing and not actually doing that well on the test are actually your top performers, well, then the test isn't really testing what it's supposed to be testing for, right? The GRE is supposed to say those with high scores, and these are the ones you want. These are the folks that we feel are going to be successful in graduate school, right? And so that's why, that's why you look for something like that. Is there a relationship between a simple field test and a difficult lab-based test for a variable of interest? Again, it's important because we can control for a lot of things in the lab, so it's important to be able to do lab-type tests. But if it doesn't necessarily translate out to a simple field test, that maybe is more representative of what somebody does, like on soccer skills or something like that, and the lab-based test is not really useful. Or the other reason you might do that is because, again, if there's a really great lab-based test, it's a great determinant of something, like this person can be successful doing this or whatever. But not everybody is privy to be able to have a laboratory and do that. If you can perform a simple field test that has a high probability rate in comparison to the lab-based test, it may not be as good, but it's a really good test, and we see a high percentage of correlation there between the two. Then that may be a great substitute for folks that are out on the field, right? So maybe something that we could give, maybe it's some type of, cognitive test for somebody who possibly has a concussion, right? Something along those lines that an athletic trainer would be able to use if he or she felt that one of their athletes might have had a concussion, right? So again, it can go both ways, how important something is in the lab, or if something in the lab will establish how important something you can do in the field would be. Differences across conditions. Is there a difference between groups? Old males and females, trained and untrained, right? Excuse me. A lot of times we want to know, is there differences? So again, we might look at, okay, what happens if men and women lift weights? Well, both men and women will, gain muscle mass. The excessive energy expenditure may help them to lose fat mass. But again, there might be differences. Males tend to be able to lift more weight the more they train versus females. They tend to get bigger. Average height and size of males is bigger. So those would be the differences. So we can see, there are similarities, but we can find differences, right? Trained and untrained. If we gave someone the same protocols that's trained versus untrained, well, the untrained folks may see greater gains because they're doing something their body's not used to, whereas the trained folks are doing something very similar to what they've already been doing, so there may not be much difference, right? And then how young and old people react to the training. Oh my gosh, sorry. You know, is there a difference before and after an intervention or treatment of some kind, right? So you can do pre-test, give a treatment or intervention, and a post-test. This is the difference. Hypotheses. So I was talking about this in the class that I went over today, which would be, it was lecture 6, right? And I was talking to him about research hypothesis and null hypothesis. So the null hypothesis is a statement indicating expectations of no relationship or no difference for purposes of statistical testing. Right, so this would be my hypothesis every time you match any diet against any other diet, as long as calories are controlled at the exact same amount. It doesn't matter if it's low carb, low fat, intermittent fasting, keto, or that's paleo, vegan, carnivore, I don't care what it is. As long as the calories are the same, you're going to see the same amount of weight loss and weight gain, depending on if you're underfeeding, overfeeding. It is what it is, right? The calories are going to be the determining factor of the weight loss, right? So if I was going to test 5 different diets, as long as I'm controlling for calories, I'm going to tell you right now, I haven't, that I believe there's a null hypothesis. I will see no difference, right? Research hypothesis is a statement indicating the researcher's true expectations as to the outcome of the study may be the same as or opposite of the null hypothesis, right? So I have a null hypothesis when it comes to diets and control of calories. I do have an opposite hypothesis, or I see that there's going to be a difference between a group that overfeeds on protein and a group that does not, right? So if we give a group that, like 3 grams per kilogram of body weight per day while they're training versus another group that does like 1 gram per kilogram, there will be a difference, right? So I hypothesize there will be a difference, okay? All right. So probability of flipping a coin, having it come up heads is 50%. Therefore, 50 out of 100 coin tosses should come up heads. However, because of error due to chance, more or fewer than 50 of 100 coin tosses may be heads, right? So again, just because you have a 50-50 chance doesn't mean that 50% of the time exactly it's going to happen, right? You could factor in things that the person's always putting heads up as they flip the coin off their thumb, right? So they do this. Maybe they get kind of in a rhythm, where it takes like 4 rotations exactly before it lands, and so those type of things may favor that it's going to land on heads more often or tails more often, slightly, because they're doing the exact same movement every time. It's only in the air for the exact same time most of the time, so on and so forth, right? So that'd be the error due to chance. All right. Alpha, level of significance, is the amount of error due to chance the researchers conducting a given study are willing to accept. So the commonly set alpha is 0.05, or what we call a 5% level of confidence. What this means for you, because you will hear anytime somebody's like, well, what was the alpha level on that particular study? Did their p-value or t-test or any, what did it come under and things like that? And you're like, I don't know what the heck they're talking about, okay? So what this means is if you have a 5% error of, like there's a 5% chance of error, right? So say the p-value, or, if they're doing a t-test, the t, any of those things come in at a number less than 0.05. So say 0.04, 0.03, 0.1, whatever that is. Okay, those are all less than 0.05. That means that there was a level of confidence that was set at 5%, and your statistics are saying that there was less chance that error was due to, less chance that whatever changes you saw or similarities you saw, difference or similarities, it was due to error of chance, right? That whatever happened in the study, so it's like 0.03, we're looking at 97% confidence that however you manipulated the independent variable and measured the dependent, it had to do with that, not to do with any type of chance or error, right? That's what that means, okay? So that's why we set those, and that's why that's our standard, typically. You'll see 0.05, some of them you see a 0.00. I think sorry, I messed up on one of the numbers I just gave you. I just realized that. I meant 0.05, 0.04, 0.03, 0.01, not 0.1. 0.1 would be 2%, right? That would actually be that thing. 0.001, things like that. You'll see, like I said, you'll see sometimes 0.05, 0.001, some of the commonly set levels of confidence, sometimes they've got to be a little bit tighter, depends on the alpha and the beta and everything. But anyways, this is the most commonly set one that you'll see in a lot of research. And so this is just saying that there's a really low chance that error caused the changes you saw, right? And it's always set before the study is conducted, okay? So probability of the results being erroneous due to chance is calculated based on the data collected. When p is smaller than that, so 0.45 is smaller than a point, or when p is smaller, so you got the 0.45 p, and actually they wrote that wrong, right? That's not actually smaller, that's actually higher. It should be 0.045, right? The null hypothesis is rejected and the results show a significant relationship or significant difference, okay? Now this one, I think was supposed to be 0.0, I think it was still supposed to be 0.055, which is higher than 0.050, but anyways, yeah, whoever put these slides together, Wolters Kluwer, if any of you guys look at this one, you guys need to fix your slides as 0.045 with the 0.05 and the 0.055 with the 0.05. The P would be greater, which means the null hypothesis is accepted and the results are not significant, right? So again, that means that there's a too high of a chance that something else played into it, right? Sometimes an error due to chance occurs in the results of the research study. There are two types. You have type 1. Results are significant when there is not a significant relationship or difference in the population. In type 2 error, the results are non-significant when there's significant relationship or difference in the population. All right. So this is what we call the truth table, how we accept and reject. So if the null hypothesis is true and you accept it, you made a good decision. If the null hypothesis is false and you rejected it, that was a good decision, right? So you'll see those in the opposite corner. So the top left and the bottom right. Okay, so top left is accepting the null when the null is true. Bottom right is accepting that it's false, or rejecting the null and the null is false. If you reject the null and the null was true, so you're saying no, it is going to be significant, and then you get like a 0.6, or a 0.06 or anything like that, and you had a 0.05 set, that means you made an incorrect decision, and it's a type 1 error, which is based on alpha. Now, if you accept the null but the null was false, this is incorrect decision. This is a type 2 error, and this is set on the beta. Okay, so we'll talk about that, what that is in a bit. Okay. So effect size, another test other than statistical significance for the meaningfulness of the results of the study evaluating the difference. A practical value for the measured difference that results from application of the treatment. The results of training program resulted in 10% change in the variable being measured at an effect size of 10%. Okay. So this is just showing how meaningful it was, right? So what was the effect of it, the effect size, right? So how much of a change was actually there, okay? Clinical relevance or importance, typically discussed when the results of a study are non-significant. The researchers attempt to make a case for the effect size being large enough that is likely to be of interest, of importance in the clinical practice. With no objective test for clinical relevance, the researcher must make the case with logic. Okay. So again, you know, you do an experiment. All right. Well, how can we use it? Right. What's the clinical relevance? You know, how important is this? You know, what does this mean? Okay. Sampling terminology. A sample is a group of participants in a research study that should represent, and they should represent well a particular population you want to study. Population is a large group with defined characteristics, you know, so again, it could be people that live in South Florida, where I'm at. It could be women that live in South Florida, men that live in South Florida. It could be Latin women that live in South Florida, African American men that live in South Florida. You know, we could look at city by city, so on and so forth, right? Those are all different populations, okay? And again, your sample should represent each one of those populations. So again, if you're trying to just do people in South Florida, you need both men and women of as many racial backgrounds as possible. Again, if you are really general men and women, you can have a lot of ages as well, right? If you want a more specific population, then you're going to have a more specific sample. Statistic, value representing a characteristic of a sample, and parameters, the value representing a characteristic of the population. Okay? So sample size, it needs to be large enough to be representative of the population. Okay? It needs to be small enough to enable practical collection of the data from the standpoint of time, supplies, availability, testing apparatus, et cetera. So that's the fight, right? You'd love to sample everybody because then that can really be generalized out. But that's not always feasible depending on what you're doing, right? And so again, it's that playing, we need it small enough that we can actually do the research, but large enough that it actually means something, right? So we calculate this to arrive at power levels, right? And so the power level we looked at is 0.8 or like 80%, where the power is the probability of correctly rejecting or accepting a null, right? So at 1, you're looking at a 95%, you know, with the alpha, and then we need an 80% basically with the power level, okay? Then, so how can you sample? It can be random. All members of a population have an equal chance of being selected. It's sort of like any of you that read Hunger Games or watched the movies. I guess that's sort of how they, you know, they randomly pick young adults and kids to, you know, do that whole thing. You know, again, sort of how they pick balls and, you know, like the shoots up. Okay. Stratified, random. All members of a designated subgroup of a population have equal chance. So again, if you were looking at African American women in Miami, again, everybody that's fits the demographic as an African American woman in Miami would have a equal chance of being selected for the study. Systematic. Every nth individual on the list is selected, so it could be every second. You know, like basically, say you have 100 people, you could do 2, 4, 6, 8, 10. It could be every third person, so third, sixth, ninth. It could be every fifth, so 5, 10, 15. You get the idea, right? And convenience is qualified, readily available participants are selected. So again, sometimes this happens, especially the more specific of the population you're looking at, right? So if you're looking at, you know, young college male, you know, athletes that participate in NCAA athletics, you're gonna have a much smaller population. So it may be, you know, the first 20, 30 guys that at your school that fit those qualifications that come in are going to be selected, right? Inclusion criteria are the characteristics individuals possess to qualify. So again, like I said, if we're looking at the, you know, like the male athletes or the female athletes, well, then they have to be on one of the athletic teams and they have to be male or female, right? Exclusion criteria are those that individuals must not possess to qualify for the participation. So you come in and it's a study on the male athletes, and a female wants to do it, well, she can't do it, you know, or vice versa, right? Or if a male comes in, but he's not on one of the athletic programs, you know, he'd be excluded. Assignment participants to groups. Random assignment is strongly, they really should have bolded strongly preferred to optimize internal validity of the study, right? Again, you don't want to have the biggest, fastest, strongest people all in one group and the slowest, smallest, weakest people in another group. That's not going to help you figure out if something works or doesn't work, right? Choice assignment by participants weakens the internal validity of the study. So if you have folks that are coming in, you know, with one group of friends and another group of friends, we'll all be together. That doesn't help with anything, right? You're not going, you know, because one group may have certain characteristics that are similar, another group have certain characteristics that are similar, and those characteristics may skew the data, okay? Levels of data, we have nominal. These are non-numerical measures labeled by name or category, so male, female, you know, would be one, you know, ethnicities, things like that. Ordinal, ranked numerical measures. So, you know, this could be anything from like fastest to slowest, tallest to shortest, you know, heaviest weight to lightest weight, so on and so forth. Interval, these are numerical quantities for which 0 does not indicate complete absence of the quantity. So again, like temperature, right? Being that we can get into negative temperatures, 0 is just another spot on the line of temperature. Ratio are numerical quantities for which 0 indicates complete absence of the quantity, right? So 3 to 1, you know, like this person can lift 3 times their body weight, things like that. Parametric is used for interval and ratio data that meet the following assumptions. The variable of interest must be normally distributed within the population. The variable of interest must have the same variance with samples drawn from the population, and scores and measures from the variable of interest must be independent. Okay? So have to meet the criteria for parametric. Right? Again, this is a normal bell curve and looking at standard deviations. Right? 99% of your population is going to fall within 3 standard deviations. 95 is going to fall within 2 standard deviations, one way or the other, from the median mode mean, and 68% are going to fall within 1 standard deviation, right? Non-parametric is used for nominal and ordinal data, as well as interval and ratio data that do not meet assumptions related to distribution in some previous slides, right? So we're going to talk about, you know, having non-bell curve looking lines now, right? So kurtosis is a vertical shift in the nominal curve such that the middle of the curve is elevated or depressed, and skewness is whether it goes left or right. Okay, so it's, you know, higher or lower on the scale, right? So kurtosis would be, you know, the peak, you know, you see that one peak to the left is very high versus the peak to the right is very low, right? It's not like one is plateaued, right? This sort of looks like what we keep seeing with predictions on coronavirus, right? You know, if everybody, you know, the thought was if they don't quarantine us, we would have had something that looked like what you see on the left with infections and deaths and so on and so forth. By making us all stay indoors, they're trying to do what's on the right, right? They're trying to flatten out the peak, so to speak, right? Positive skewed versus negative skewed. Again, positive skewed has the tail going to the right. Negative skewed has the tail going to the left, okay? All right, so that's that for chapter 10. If you have any questions, please email me or text me, and I'll be happy to answer those. And that is it for this chapter. I'll stop recording.